Assalamu alaikum dear students. I welcome you to 28th lecture of probability and stochastic processes. In previous lectures, we finished our discussion of transformation of random variables and moved on to investigation of mean, variance and other moments of derived random variables. The idea behind this investigation is that we want to relate the mean, variance and other moments of derived random variables with moments of underlying random variables. When we were transforming underlying random variables to new transformed random variables, we did a complete analysis of the behavior of the transformed random variable through its PDF. If we find the PDF of derived random variable, we have complete information about its unpredictable behavior. We can use that PDF to find the mean, the variance and other moments of this derived random variable. But the idea is to find these moments of derived random variables from the joint PDF or individual PDF of the underlying random variables, and by using the transforming functions which relate underlying random variables to transformed random variables. If we knew the PDF of derived random variable, it's straightforward to find mean and variance and other moments of derived random variable, just as it is so straightforward to find the mean, variance and other moments of underlying random variables if we knew the PDF of underlying random variable. So if you are only interested in finding the moments, mean, variance and other higher moments, or expected value of any function of derived random variable without using the PDF of derived variable, we can do that by using the PDF of underlying random variable and the transforming functions which are used to relate derived random variables and underlying random variables. Let's see on the screen a few equations which form the basis of the procedure that I just outlined. So the basic idea is that we want to find the expected value of function of u and v. So if we want to find the expected value of u, we'll just use u. If we want to find the expected value of v, we will just use v. If we want to find the second moment, the regular one, we'll use u square or v square. And if we want to find the centralized moment, you will use u minus the mean value of u whole square. We can use any function of u and v, and we can find the expected value of the function of u and v using the joint PDF of x and y and not the joint PDF of u and v. Have a look at this first equation, which says that if you want to find the mean value of u, mu u, which is expected value of random variable u, the first well-known method is that you integrate the PDF of u and multiplication of this PDF with u over the whole range of u. But you can use joint PDF of u and v to find this expected value of u, and then you have to use the double integral. We went through this last time, and the argument is that if we take this joint PDF of u and v and integrate it with respect to v, you will get this marginal PDF of u. Hence, u times joint PDF of u and v and double integral over the whole uv plane will also give you the mean value of u. And if you replace all these quantities in terms of the joint PDF of x and y, these two integrals are equivalent, where instead of the joint PDF of u and v, we have used joint PDF of x and y, and instead of u, we have used g of x and y. That is the transforming function which takes values of x, values of y, and replaces them with value of u. So this u is replaced by this transforming function of x and y. this joint PDF with the original PDF, and this integral is equal to this integral. Hence, if we want to find simply the mean value of u, you can use this expression with joint PDF of x and y and the transforming function of x and y to u. Let's look at the next equation. Suppose you form a new random variable w, which is related to random variable u through this transforming function r. So this transforming function r takes value of u as its input and gives out a new value, which is value of random variable w. So w is a transformed random variable obtained from transformed random variable u. So this r is a function from set of real numbers to set of real numbers. Hence, if you want to find the expected value of w, which is a transformation from u through this function r, you can still use the joint PDF of x and y. You don't have to find the PDF of new transformed random variable w. The idea is that you use g, which takes values of x and y, and it gives you value of u. And you take this value of u and transform it to value of w through this function r. So this double transformation can be used in conjunction with this joint PDF of x and y to find the expected value of w. So if you want to find expected value of w, which is expected value of a function of u, ru, and then with joint PDF of x and y, you will use r of g of x and y. So there is a cascade of two functions. First function g takes on values of x and y, gives you a value of u. So this value of u is transformed through r to give you a value of w. So this whole thing is value of w, and using this joint PDF through all these cascade of functions, you are effectively finding the expected value of w, which is a function of u, using joint PDF of x and y and this double cascade of functions g and r. And if you have to find the expected value of any general function r, which is a function of both u and v, you can take this function r, and instead of u and v, you put the functions which are functions from x and y to u, which is g, and x and y to v, which is h. So this function and this function are used as two arguments of this function r, and this complicated combination of g, h, and r can be used in conjunction with this joint PDF of x and y to find the expected value of a general function of u and v. So if you are interested in finding the expected value of any derived random variable or expected value of a function of derived random variable, you don't have to find the PDF of derived random variable. You can use all the functions involved in transforming underlying random variable into derived random variable in conjunction with the PDF of underlying random variable, and you can get the expected value of any general function of a derived random variable or more than one derived random variables. Now let's look at the example that we started looking at in the last lecture, that is the linear transformation. So if we have a pair of underlying random variables x and y, and we define two transformations g and h, where g takes on values of x and y and gives you value of a new random variable u, and h takes on values of x and y and give you value of a new random variable v. But these transformations g and h are linear. They involve single power of x and y, which can use coefficients, but it is a linear combination of x and y. So g can be alpha times x plus beta times y, where alpha and beta can be any real numbers. Similarly, v can be equal to h of x and y, where h is a function which can be gamma x plus delta y, where gamma and delta can be any real numbers. So if you take this linear transformation, you can have two random variables u and v, which are derived from two random variables x and y through a pair of linear transformations g and h. And this can compactly be represented using matrices. So this is the value of u, which is equal to alpha times x plus beta times y, and value of v is gamma times x plus delta times y. So these two equations, which take two random variables x and y and give you two new random variables u and v, can be compactly shown as matrix multiplication. X and y are entries of this column matrix or column vector, and this is the transforming matrix. So if you multiply this transforming matrix alpha, beta, gamma, delta with this row multiplies this to give you this value. So alpha times x plus beta times y is u. Similarly, gamma times x plus delta times y is v. Exactly the equations that we started with, the equations of our pair of linear transformations g and h. This is g, this is h, both are linear, and their transformation of x and y to u and v is compactly shown here as matrix multiplication. If this is the case, then we would be interested in finding the mean, variance, and other moments of transformed random variables u and v in terms of mean, variance, and other moments of x and y without having to find the joint PDF of u and v. By the way, for this kind of linear transformation, it's easy to find the joint PDF of u and v, but we would like to avoid that step. So if you want to find the mean value of u and v, this is a simple expression which shows that mean value of u is expected value of u, where u is simply alpha x plus beta y. And this is a general function of x plus y. So if you want to find expected value of this general function of x and y, because of expectation being a linear operator, this simply comes out to be alpha times mean value of x plus beta times mean value of y. Similarly, mean value of v is expectation of this function of x and y, and this gives us that mean value of v is gamma times mean values of x plus delta times mean value of y. You can see the similarity between these two equations and these two equations. Here xy were the underlying random variables which were combined using this pair of equations to give you two new random variables u and v. Here again alpha mu x, beta mu y, gamma mu x, delta mu y. So mu x, mu y are the things which are getting combined using the same coefficients to give you two new things. So this can also be this transformation of mean values of x and y, which are used combined to give you mean values of u and v, can also be represented in matrix form. So mu u mu v, which is a column vector, is equal to transformation with the same matrix of old mean values of mu x and mu y. So if we compactly represent this transforming matrix with A, then this column vector, when multiplied with this matrix A, gives you new mean values of derived random variables u and v. So it is easy to get the values of means of transformed random variables u and v from the transforming matrix A if transforming matrix A is used to define u and v from underlying random variables x and y. Now let's have a look at the variance of u or v, how they are related to variance of x and y. So if you want to find variance of u, this is the expression which we generally evaluate, which is expected value of u minus mean value of u whole square. Now, a few slides ago, I showed you that you can find the expected value of any function of u and v using the underlying PDF of x and y. Actually, you don't have to do that. You just expand this intelligently and you can see how things are related to each other. This mu u, which we just evaluated, is a constant. Its mean value of u, and it is related to mean value of x and mean value of y through that linear combination, and we already know that. Now, if you expand this and combine different terms, it turns out that this expression is equal to expected value of simply u square. U is a random variable, so if you take expected value of u square, you have to evaluate that. So this is the new function of u whose expected value you have to find. This is already known, so this already known quantity squared is also known quantity. All you have to do is find the expected value of u square. And if you expand the expression of u, which is alpha times x plus beta times y, you take square of that term, it turns out to be alpha times x square plus beta times y square plus 2 times alpha beta and then x into y. So if you take expected value of all these terms, it turns out that sigma square u, the variance of u is equal to alpha square times sigma x square plus beta square times sigma y square plus 2 alpha beta correlation of x and y minus mu x minus mu y. And if you look carefully at this expression, this is nothing but covariance of x and y. So if you want to find the variance of derived random variable u, which is defined through a linear transformation from x and y, this is the expression for the variance of u. It involves variance of x, it involves variance of y, which gets scaled by alpha square and beta square, but it also involves the cross term, the covariance between x and y, and this gets scaled up by 2 times alpha times beta. So if we have a linear transformation which takes values of random variable x and random variable y, combines them in a linear manner to give you value of u, you can find the variance of u by expanding the expression of u in terms of the linear transformation of x and y and taking the expected values of all the relevant terms to get an expression which involves variance of x, variance of y, and the cross term which is covariance of x and y. Let's have a look at the expression of variance of v, the other random variable which we have through another linear transformation h, which is gamma times x plus delta times y. This expression is very similar to the previous one. Here, if we want to find the expected value of v minus mu v whole square, which is variance of v, you can expand it in similar manner and you will get an expression which involves variance of x, variance of y, and again covariance of x and y, but the coefficients have changed because this comes from a linear transformation involving gamma and delta. The coefficients are gamma square for sigma x square, delta square for sigma y square, and 2 times gamma times delta for covariance of x and y. So it's easy to see how a linear transformation can be used to find the mean values and variances of a pair of transformed random variables in terms of mean values and variances of the underlying random variables, with one interesting observation that when you are finding the variances of transformed random variables, the expression involves not only the variances but the covariance of underlying random variables. Let's go ahead and find the correlation and covariance of transformed random variables u and v in terms of the mean, variance and covariances of random variables x and y. So if you want to find the correlation of u and v, the transformed random variables, this is what you want to find, expected value of u and v. So u and v, multiplication of the two, is the generalized function whose expected value you want to find. If you expand these terms, you will get alpha times gamma times x square plus beta times delta times y square, and then cross terms alpha times delta times xy, beta times gamma times xy. If you combine all these terms, you get this, which is an expression involving three expectations: expectation of x square, expectation of y square, and expectation of xy. So you are finding the general second moment of x, general second moment of y, and correlation of x and y. Generally, we are more interested in covariance of two random variables than the correlation, because covariance is using the centralized cross moments. So let's see the expression of covariance of u and v, the two derived random variables. After simplification, you know that covariance of u and v is this correlation of u and v minus the multiplication of mean values of u and mean value of v. These quantities are known. This is also known. This is simply three expectations. So if you substitute all the required values, then covariance of u and v comes out to be alpha times gamma times variance of x, beta times delta times variance of y, and then this coefficient alpha delta plus beta gamma times the covariance of x and y. So you can find all the moments for u and v, the mean, the variance, and covariance in terms of mean, variance, and covariance of x and y. If you look carefully at the expressions of variance and covariance, you will realize that they are both moments of second degree. When you are finding the variance of a random variable, you are finding the expected value of multiplication of two expressions, where both expressions are same and they are x minus mu x, or any random variable minus its mean value. And when you are finding the covariance between two random variables, then you are finding the expected value of multiplication of two expressions again, where first expression is x minus mu x and second expression is y minus mu y. Or you can have any two random variables instead of x and y, you can have u and v. In that case, it will be expected value of two expressions. One is u minus mu u, other is v minus mu v. So variance and covariance of two random variables are moments of second degree. And there are four of them. There is variance of first random variable, variance of second random variable, and covariance between two, where first random variable is in the first position and second is in the second. Or you can swap the two, but it does not make any difference. So covariance is used as a third element of this collection. So if you want to arrange these second degree moments in a matrix form, you can have, which is called a covariance matrix. If you have two random variables x and y, or u and v, your covariance matrix is a 2 by 2 matrix, where the entry in the top left corner, the 1 1 location, is the variance of first random variable. The entry in the 2 2 corner, the bottom right corner, is the variance of second random variable. And the two off diagonal entries at 2, 1 and 1, 2 are covariance between the two random variables involved. So this collection, which is put in the matrix form, is called covariance matrix, and it summarizes the behavior of second degree moments of two random variables involved. Let's have a look at the screen to see what this means. If we have two random variables x and y, then sigma x square, variance of x, sigma y square, variance of y, and these two terms are covariance of x and y. One interesting observation is that if covariance of x and y is 0, that is, the two random variables x and y are uncorrelated with each other, then these entries will be 0 and this matrix will be diagonal with variance of x here and variance of y in the bottom right position. Instead of random variables x and y, if we had random variables u and v, we can find the covariance matrix of random variables u and v, which will be k of u and v. In that case, you will have variance of u here, variance of v here, and covariance of u and v in these off-diagonal conditions. We have already found the expressions for variance of u, variance of v, and the covariance between u and v in terms of variance of x, variance of y, and covariance of x and y. But in this case, we have made a simplifying assumption that the random variables x and y are uncorrelated. In that case, covariance of x and y will be 0. If we put this covariance of x and y equal to 0 into the expressions for variance of u and variance of v and covariance of u and v, we will get a simplified version of covariance matrix of u and v. Let's have a look at that simplified version of covariance matrix of u and v. So under this assumption that covariance of x and y is 0, the expression for variance of x and y does not contain that cross term. The variance of x and y as used to get variance of v does not contain the cross term. Similarly, the covariance of u and v as expressed in terms of variance of x, variance of y does not have that cross term. So this is an expression for covariance matrix of u and v in terms of variance of x and variance of y. Even with this simplifying assumption that covariance of x and y is 0, which transforms this covariance matrix to this simplified covariance matrix, the covariance matrix of u and v is still a complicated expression which involves variance of x, variance of y everywhere. So the question is there a relationship between the covariance matrix of x and y and covariance matrix of u and v under the simplifying assumption that covariance between x and y is equal to 0? If you look at these two matrices, there doesn't seem to be a clear relationship between the two. But there is one interesting observation that in all the four entries, these entries get combined. So you will see sum of sigma x square and sigma y square, but the coefficients are not single coefficients as the case was when we found the mean values of transformed random variable in terms of mean values of underlying random variable. There are two of them. Everywhere you either see alpha times gamma, multiplication of two coefficients of transforming matrix A, or gamma square, the square of one of the four transforming coefficients. So this gives us an idea that perhaps somehow there are two transformations going on, because the coefficients which combine sigma x square and sigma y square to give you different entries of covariance of u and v have two coefficients multiplied with sigma x square and sigma y square before they get combined. So there are two transformations. There is one transformation which introduces alpha, beta, gamma and delta next to sigma x square and sigma y square, and there is another transformation followed by that which again introduces these alpha, beta, gamma, delta. So you will see alpha square, beta square, alpha times gamma and beta times delta. This careful observation is important, and based on this information we can actually find the relationship between covariance matrix of x and y and covariance matrix of u and v under the simplifying assumption that covariance between x and y is equal to 0. So this transformation of covariance matrix of x and y into covariance matrix of u and v perhaps involves two transformations using the matrix A. And on the screen you can see what we are after. We want to get to this covariance matrix of u and v by transforming this covariance matrix of x and y through some transformation, which perhaps involves two transformations with transforming matrix A. So what this transformation is, it turns out that this transformation is of this form. This covariance matrix of x and y is in the center. This gets multiplied here with matrix A, the transformation matrix which takes x and y and gives you u and v. And the whole result gets multiplied with this matrix which is transpose of this. Instead of alpha beta, we have alpha beta here, and instead of gamma delta as second row, we have gamma delta as second column. So this is how these two transformations are used to transform covariance matrix of x and y into covariance matrix of u and v. And this can compactly be represented as multiplication of A and covariance matrix of x and y and A transpose. You can multiply these in any order. You can multiply these two together and then multiply with this. You can multiply these two together and then multiply with this, but you have to follow the rules of matrix multiplication. So this A times covariance matrix of x and y times transpose of A matrix, that is called a quadratic form of matrix multiplication. The matrix A gets multiplied with covariance matrix of x and y twice. When it is being multiplied before the covariance matrix, it is A, and when it is multiplied after the covariance matrix, it is A transpose. And the combined result is that you get a covariance matrix of u and v which involve summations of sigma x square and sigma y square, but the coefficients of these summation are not single coefficients alpha or beta or gamma or delta, but always two of them, alpha times beta or gamma square or alpha times delta, etc., etc. Now that we know how to get to the covariance matrix of u and v, the pair of transformed random variables, from covariance matrix of x and y, the pair of underlying random variables, let's look at a few simple examples of getting to covariance matrix of u and v from covariance matrix of x and y. Here is the first example where kxy is given as 1, 0, 0, 1. So here, as we assumed under the simplifying assumption that covariance between x and y is 0, variance of x is 1, variance of y is also 1, and here is our transformation matrix A. So the two random variables u and v are obtained from x and y using these equations. So u is 2x plus y and v is x plus 2y. These are simple linear transformations to get u and v. But we want to find the covariance matrix of u and v. So this is alpha, beta, gamma, delta using these values and this value of sigma x square, sigma y whole square. You get to this matrix which is covariance matrix of u and v. And if you look carefully at all these terms, you will see that variance of u is now 5. Variance of v is also 5, which is 5 times the variance of x and y. Not only that, there is covariance between u and v. The value of covariance is quite high, it is 4. So from this pair of uncorrelated random variables x and y, where covariance is 0, under this simple transformation, you get a random variable pair uv where variance of u in v is 5 times the variance of x and y, and the uncorrelated pair of random variables x and y has been transformed to a random variable pair of u and v which are not uncorrelated, which are correlated, and this is the value of correlation. Let's look at the second example. In this example, the covariance matrix is same. There is no correlation between x and y, so x and y are uncorrelated, and here is the transforming matrix. This transforming matrix should remind you the derived random variables u and v we used during the example we worked on 2 television. So this is u, which is x plus y, which is the sum of service times. This is v, which is x minus y, which is the difference of service times. So if we are trying to find the covariance matrix of u and v, where u and v represent sum of service times of 2 televisions and difference of service times of 2 televisions, we can find what the variance of u, variance of v, and possibly covariance of u and v is by knowing the components of linear transformation, which is 1 and 1 for x plus y, and 1 and minus 1 for x minus y, and the variance of x and variance of y. So if you use all the coefficients alpha, beta, gamma, delta, and sigma x square, sigma y square, this is what you get. So in this particular case, the derived random variables u and v, where u represents sum of service times, v represents difference of service times, they are uncorrelated with each other. Not only that, the variance has gone up by a factor of 2. So if variance of x is 1, variance of y is 1, variance of u is 2, variance of v is also 2, but they are still uncorrelated. So if you start from a pair of uncorrelated random variables and use linear transformations, sometimes you get pair of derived random variables which are correlated, and sometimes you get pair of derived random variables which are uncorrelated. And if they are uncorrelated, the value of variance of derived random variables and value of variance of underlying random variable is also a factor of this. How? Let's look at a slightly different example where I have taken this transforming matrix and divided all the entries by square root of 2. With this simple change, the covariance matrix of u and v is also identity matrix where variance of u is 1, variance of v is 1, and they are still uncorrelated. So if these entries are carefully chosen, you can have this covariance matrix of derived random variables same as the covariance matrix of underlying random variables. Let's look at the last example. Here, this transforming matrix is same as this one, which represents sum of service times and difference of service times, but the characteristics of underlying random variables x and y are such that sigma x square is 2 and sigma y square is 1. So we are dealing with an example of 2 televisions where the behavior of 2 television is uncorrelated, but the variance of 2 televisions or variance of the service times of 2 television is different. Actually, this was exactly the case when we were working with 2 televisions. We assumed that 2 televisions were manufactured by 2 different manufacturers and they followed 2 different PDFs. When the PDFs were different, the mean values were different and the variances were also different. So if the failure mechanism of 2 television was such that they fail independent of each other, which implies that they were uncorrelated, but the variance of their service times were different, and we transformed the service times to 2 new random variables, sum and difference, this is what we get. So variance of x is different from variance of y, they are uncorrelated, and you use the same transforming matrix as we used here, you get a covariance matrix of u and v which has same value here and here. So variance of u and variance of v is same, but there is some correlation. So if you compare this case with this case, you will see that we use the same transforming matrix A, but in this case the variances were same, and you get a covariance matrix of pair of derived random variables, which gives you uncorrelated derived random variables. Using the same transforming matrix, but using the two underlying random variables with different values of variances, you get two derived random variables which are correlated. Uncorrelated because of this special nature of the variance of two underlying random variables, and correlated because of this change in the behavior of underlying random variables, that their variances are different. So the most important point to get from this discussion is that if you start with a pair of uncorrelated random variables x and y and use a linear transformation, which is a matrix comprising of two transformations g and h, and get two new random variables u and v, then it is quite possible to have these new random variables correlated. So you start from a pair of uncorrelated random variables, use linear transformation to get to a pair of derived random variables which are correlated. Can reverse also be true? That is, if you start from a pair of correlated random variables x and y and use a linear transformation and reach to a pair of derived random variables u and v which are uncorrelated. The answer to this question is yes. Yes, we can start with a pair of correlated random variables and through a linear transformation get to two derived random variables which are uncorrelated. But the bigger question is, why we want to reach to a pair of uncorrelated random variables? The answer is that if the two random variables that we are working with are uncorrelated, it makes easier for us to make some decisions about their behavior. If we want to make a decision about their behavior based on the observations of only one of the two random variables and they are uncorrelated, this observation is uncorrelated with the observations of other random variable, then we can make the decision solely based on the observation of this one random variable. But if they are correlated, we have to look at both observations and make a decision based on the observation of both random variables. So if you have a pair of correlated random variables, how do you design a linear transformation so that the pair of transformed random variables becomes uncorrelated? The answer lies in the idea of eigenvalues and eigenvectors. Before going to eigenvalues and eigenvectors, let's have a look at the covariance matrix of transformed random variables u and v without that assumption that x and y were uncorrelated. So even if x and y are correlated and covariance between x and y is non-zero, we still have the expressions for variance of u, variance of v, and covariance between u and v. We'll use those expressions to find the covariance matrix of u and v, which comes out to be of this form. Here, the covariance matrix between u and v has this term plus this term. Under the simplifying assumption, this term was absent. Similarly, the variance of v had these terms, but without that assumption, you have to add this term. Similarly, the covariance between u and v has these two terms and this cross term. So if you look at this matrix, which is more complicated than the matrix for covariance between u and v under the simplifying assumption that this covariance between x and y and 0, this more complicated matrix also has a connection with covariance of x and y without the assumption that this term is 0. And this connection comes out to be exactly the same as the previous one, that you have the same transformation which is quadratic in nature, where this A multiplies with this covariance matrix of x and y without making these terms 0, and the results get multiplied with this A transpose, where alpha beta becomes a column instead of a row, and gamma delta, which is row here, becomes a column here. So if this covariance matrix of U and V has this expression which is equivalent to this expression, then the question is, if we start with this covariance matrix of x and y with non-zero entries here, can we design our transformation matrix A, which is used here, and in its transpose form used here, in such a way that the result of this whole thing, which is covariance of U and V, has only terms in top left and bottom right corner. In other words, I would like to have this term present, but I would like to have this term absent and this term absent, and I would like to have 0 here and 0 here. Can we do that? The answer is yes, and the answer lies in the idea of eigenvalues and eigenvectors. So let's quickly review this idea of eigenvalues and eigenvectors. To understand the idea of eigenvalues and eigenvectors, you should know the rules of matrix multiplication. A matrix in general is a rectangular grid of numbers where a specific number is at a specific location. A matrix can be square with as many rows as there are columns, or it can be rectangular where number of rows can be different from number of columns. And in the extreme case, it can have only one row, in which case it is called a row matrix or row vector, or just one column, in which case it is called a column vector or column matrix. Now suppose you have a square matrix of size n by n rows and n columns. If you want to multiply this with a column matrix or column vector, then column vector has to be on the right side. So n by n matrix multiplies with n by 1 column vector, and the result is a new column vector of size n by 1. So in other words, an n by n vector has been transformed through matrix multiplication to a new n by 1 column vector. In general, these two column vectors are different, but sometimes for some specific column vector, it's possible that the result of the transformation is such that it is a scaled multiple of the original column vector. If that's the case, then this column vector is called eigenvector of the transformation matrix, and the scale multiple is called eigenvalue. Let's have a look at a simple example. We have a 2 by 2 matrix T with entries T11, T12, T21 and T22. And suppose we have a column vector A, and if we transform this column vector through multiplication, we get a transformed vector TA, which is equal to lambda A, lambda times A. Then this lambda is the eigenvalue and this A is eigenvector. For non-trivial 2 by 2 square matrices which are invertible, there are two such eigenvectors and corresponding two eigenvalues. So if the two eigenvectors are A1 and A2, then transformation of A1 will be lambda 1 times A1 and transformation of A2 will be lambda 2 times A2. Similarly, for an n by n square matrix that is invertible, there are n eigenvectors and corresponding n eigenvalues with special relationship that if any of the eigenvector is transformed through that transforming matrix, the result is a scale multiple of the original column vector. We can use this special property of eigenvectors and eigenvalues to design linear transformations such that if the original pair of random variables is correlated, the transformed pair of random variables is uncorrelated. How we are going to do that? We'll cover that in next lecture. To review what we covered in today's lecture, we started with the relationship of mean, variance and other moments of underlying pair of random variables with mean, variance and other moments of transformed random variables. We found that a special linear transformation which transforms the underlying random variables to transformed random variables through simple linear relationships is very nice in a way that if the underlying random variables are uncorrelated, the derived pair of random variables usually are correlated unless there are some specific characteristics of the transformation. And the reverse is also true, that if the underlying random variables are correlated, you can design a linear transformation in such a way that the pair of transformed random variables is uncorrelated. This is achieved through the properties of eigenvalues and eigenvectors, and detail of this procedure will be covered in next lecture. Till then, I wish you the best. Thank you. Khuda Hafiz.